thing I want to do, well, you know what, we're going to start in on this today, so. Really get ease out. But before we do that, we closed really quickly last time with a discussion of just interest rates as an application of exponential stuff. And here are the formulas we got. If you stick some initial investment, some principal, in an interest-bearing account, that advertises an annual interest rate of R, compounded n times per year, and you leave it in there for a total time of t years, then the amount you have after that time is principal times 1 plus the interest rate divided by n. So I write like, if the annual interest rate is R and you're applying it n times each time, you should like only apply an nth of it. That's why you divide by n. Then how many times do you apply it? N times per year, t years have passed. So let's use that and make some computations. The idea is we're going to see something limiting happening. As we plug in bigger and bigger values for n, it won't keep growing without bound. It'll seem to get close to a specific something. And let's see that specific something. So let's make some computations. If the principal is 150, interest rate is 5%, you leave it in for t equals 10 years, and you vary how many times you compound per year. Let's just see what behavior we get. So, doing that, okay, fine. Let's do that. So 150 is the initial principal times 1 plus 0.05, and then we divide by n. And now let's look to this particular example. What is n in this next example I want to do? 365. Parentheses matter. And then I want to take all that and raise it to the 10 times 365. So we get about 247.2997. And let's just go ahead and compare. From 12 times per year to 365 times per year, did the payoff increase? By much? Nope. Let's ratchet it up some more. What if we do 10,000 times per year? So how will the thing that I need to ask the calculator to do change to do this? Yeah, the thing that used to be 365, so the n, will become 10,000. So 1 with 4 zeros. Did it increase? Not by much, but it did increase. 247.307, and I guess that rounds up to a 9 now. Oh no, that's right. So it went up by more than a penny. Let's increase it further. Instead of 10,000 times, let's do 100,000 times. Did it increase? By much? Is it by enough that I can even tell the difference at the number of digits I'm recording? Maybe not the number of digits you're recording, but I'm going out to the 100th of a penny. I can still see that. 247.3081. 1/10 of a penny increase. Let's add some more zeros. Next one is another 1 0 on top. Did it go up? Not by much. So it seems to continue to increase, but it stabilizes. As that parameter n grows, it looks like it's bumping up against some like maximum value that it takes. that maximum value is this. The formula for continuously compounded interest is just the principal times e to the RT. So you should be thinking of this as like what happens when you plug in a really huge number for the number of times you compound for n. And let's just check that in this particular case. So same principal, 150 times e to the same interest rate, 0.05 times 10 years. Let's see what we get. 150 times Euler's number raised to the 0.05 for 5% times the number of years, 10 years. Do we get pretty close to that? In fact, it's, well, it's not going to be exact. That one rounds up to a 2. Neato. So, in reality, this is the origin of what Euler's number is. You start thinking about what the natural thing to do if you want to compound an interest rate more and more times per period. As the number of times you compound goes up, you get to some stable behavior. It's Euler's number that shows up. Cool. Folks feel pretty good? Nice. How many people had already looked at the homework that was assigned on Monday? This look pretty familiar then? Yeah. The homework is basically this. Do this verification. Groovy. So I want to introduce now an entirely different topic from what we've been doing so far. We're going to start waxing this class way more geometrical. We're going to start talking about angles and triangles and circles. We're going to start doing trigonometry. So let's say what the things that are at the heart of trigonometry. What is trigonometry? Trigonometry is the study of the two functions that I'm about to describe. Sine and cosine. They take as their parameter some number theta, which you're going to think of as an angle. Here's the description. So start at the point 1, 0 on the unit circle. So start at the point on the unit circle that sits on the positive x-axis, and then start rotating in the positive direction. So that's counterclockwise. You rotate up by that angle theta. You'll land at some point. That point will have some xy coordinate. Cosine of theta is the x coordinate of that point. Sine of theta is the y coordinate of that point. So let's just go ahead and think about this for a second. Does that seem to describe a function? Is it a set of instructions that starts with a number as the input and then gives you a number as the output? Yeah, so this is a function. It's absolutely not defined in an algebraic way right now. Right now, if you wanted to determine trig functions of some angle, you'd have to take out a compass and a ruler, I guess. Try to actually measure coordinates on a circle. And that's one way to do it. We'll do some geometry to figure things out with more precision. There's one thing that I want to do before we can do any of that. If I give you a number, how do you think of that number as being an angle? And I'm like, that's not clear. If I said I want you to think of an angle of 5, how many people would assume I mean 5 degrees? Yeah, I mean, but I won't mean 5 degrees. There will be a different angle measure that I'd rather use. Well, let's talk about degree measure first, because that's when you know. So, before we can do any of this really, today will be all about just how do you measure angles. And here's the first way, degrees. So, everyone's heard of a degree, right? That's how, most sciencey things measure angles. What does 1 degree mean? 1/360th. Yeah, of what? Like a circle. Yeah, it's 1/360th of the full circle. So, when someone says they want to think of an angle of 1 degree is 1/360th of, I won't say a circle, I'll say a full revolution, but tomato potato, I guess. So what's the idea? Take one full revolution, you break that up into 360 equally sized pieces. Each of those pieces is 1 degree in size. So let's just see one other thing. How much of a full revolution then should 90 degrees be? Quarter. And on the one hand, like, you know what 90 degrees should be. Yeah, that's a quarter of a full revolution. On the other hand, it should be, let's see, 90 degrees, and each degree is 1/360th of a revolution. So 1 revolution per 360 degrees. The units of degrees cancel, you wind up with 90 360ths of a revolution. Yeah, that's 1/4. Good. So if you want to measure things in degrees, well, you're just saying, well, what? If you break a circle up into 360 equally sized pieces, how many of those pieces are you using in this angle? And there are upsides and downsides to using degrees. Maybe I'll say like the origin of why 360 pieces. The origin is because the Babylonians liked the number 6. Same as the reason like we like the number 10. So if this were like defined more concurrently, maybe a degree would just be 1% of a circle. There's no reason not to do it that way. I'd like to next give a way of measuring angles which does have a reasoning behind it. I'm not going to arbitrarily say, I'm going to say 1 unit is this fraction of a circle. I'm going to do some geometry to define these angles. Let's talk about radian measure. Radian measure. So, let's draw a picture. If you start on a circle of radius r, so there's the center of the circle, the radius of the circle is r. If you walk counterclockwise on this circle, some assigned distance s. So walk until you've covered a total of s feet as you walk around this circle. Well, hey, then you've just traced out an angle, right? This angle has radian measure s divided by the radius. So now that it's drawn, let's also like fill in the words. So stand on a circle of radius r. If you walk counterclockwise until you've covered a total distance of s, then you have traced out an angle of s divided by r radians. So, radian measure isn't based on like breaking a circle up into any number of equally sized pieces. It's just based on the idea of how far do you walk around the edge of the circle if you trace out this angle. And suddenly that's like all geometric. There's no arbitrary choice made. And yet we can still like measure angles. If you have a circle of radius 2 centimeters and an arc length of also 2 centimeters, then what is this radian measure? 1. Why 1? Because 2 divided by 2 is 1. Maybe I'll even put the units in. So, radian measure is equal to s, which is 2 centimeters right here, divided by 2 centimeters. Yeah, anything divided by itself is always 1. Cool. That seem all right? What about that next angle? What is it? What you said sounded right, but it was very faint, and it sounded like there was a question mark at the end.
4 radians?
That's a now fully enunciated and sounding confident. People agree? Agree. decimals, it'll be 6. It's all in centimeters, so we can suppress the units. If I did something silly like saying this was 6 centimeters on a radius of 1 inch, how would that change the problem? You need to do like some unit convolutions, right? So if I changed it to this problem, you'd say, well, this theta is, same thing, S over 6 centimeters divided by 1.5 inches. And I guess we should either convert those inches to centimeters or centimeters to inches. Anyone know the conversion from centimeters to inches just off the top of their head?
Inches to centimeters is 2.54.
2.54 centimeters to an inch. Oh, cool. And I guess that's probably approximate because the units aren't actually consistent enough to like be rationally related. But let's just use that. So let's get rid of one or the other. Let's multiply by 2.54 centimeters is 1 inch. So 1 inch is 2.54 centimeters. So what have I done there? I just multiplied by 1 in a cleverly chosen way. Because the numerator and denominator are equal, at least if you gave me the right unit conversion. In general, though, if you like don't know a unit conversion, you have access to like the internet, right? Yeah, you can use it. All right, does that look like something we could still compute? Yeah, and the inches will now cancel. Centimeters will cancel. And now, those numbers are ugly enough, let's use a calculator. 6 divided by 1.5 times 1 divided by 2.54. $1.57. It's groovy. How do folks feel? Pretty okay so far? Whenever you want to compute radian measure of an angle, just do arc length divided by radius. That is the definition. And if someone's done something silly with units, then you just have to account for that. All right, so here I think is my next goal. We have 3 reasonable ways that, well, 3 ways that you might measure an angle. We might give you a degree measure. Right, there are upsides and downsides to degree measure. Angles you expect to see will be like between 0 and 360. It's like a not unreasonable range of numbers that you'll see in radians have an advantage that they geometrically mean something. So if you do anything with the geometry using that angle, that answer will be nicer if you put it in radians. You can also just straight up measure what fraction of a full revolution is this angle. Those are 3 perfectly reasonable ways to measure angles. Let's get conversions between them. And one thing we already have, how many degrees is a full revolution? A lot of whispering of 360 degrees? Yeah. And that's just like a fact. That's how degrees are defined. Let's figure out how many radians is 1 full revolution. Yeah, what do you think? I hear a 2 pi. And let's actually see why. See why that's the radian measure of all the way around the circle. Yeah, you just said the world circumference, right? Yeah, that is the reason. Let's do that. So, let's figure out what 1 full revolution is. So to do that, we'll start at the point 1, 0 on a circle of some radius. I'm not going to specify the radius. The radius will be r. Let's walk all the way around the circle. So that's 1 full revolution. I want to compute the radian measure of that angle. That means I need to do s divided by r. I know what r is. R is the radius. What's the circumference of this circle? What's the circumference of a circle of radius r? 2 pi times the radius? Yeah. And that's just like a bit of geometry that hopefully even if you didn't remember it off the top of your head, you remember seeing at some point that fact. All right, so that means that the radian measure is s divided by r. I know what s is. It's 2 pi times the radius divided by the radius. Oh yeah, that's 2 pi. 1 revolution is 2 pi radians. All right, so just like how to convert between centimeters and inches, you just need to know what one measurement is in the opposite language. This gives us that. 360 degrees is equal to 2 pi radians. We can use that to get a conversion factor. We can use that to convert between radians and degrees. So, let's do that. Let's try to convert degrees to radians. So let's start with an angle of d degrees. And I'll try to multiply by 1 in appropriate ways over and over again. So I'm going to try to fill in things so that that fraction is just 1. How many degrees makes 1 revolution? 360. So that thing is now just 1. Thing on the top is equal to the thing on the bottom, so that fraction is 1. How many radians makes 1 full revolution? 2 pi by the thing we just did. So that total is just 1. So whatever this is, it's still equal to d degrees. Some units going to cancel now? Yeah. First fraction was chosen so the degrees cancel. Second fraction is chosen so revolutions cancel. So this looks like it is d times 2 pi divided by 360 radians. And I'm going to use that result an awful lot for the remainder of the semester, whenever I want to convert from radians to degrees. And if I'm going to use it so much, I should simplify it. Numerator and denominator have any common factors? 2. So let's cancel that common 2. I guess I'll just wind up with, so it'll be d times pi divided by 180, I think? Yes. So whenever you want to have an angle of d degrees, you'd like it to be in radians, which will be an awful lot of the time. There's how you can multiply by pi divided by 180. Do you think we could probably go the other way? Mm-hmm. And on the one hand, we could like fill in that same table, but maybe we'll just try to intuit something. So to go from degrees to radians, you multiply by d, then you multiply by pi, then divide by 180 to go from degrees to radians. What you do if you want to go the opposite direction. What's the opposite of multiplying by pi and then dividing by 180? Dividing by pi and then multiplying by 180? And I guess it doesn't matter what order you say those two things in. So, if you have an angle of theta radians, you'd like to convert it to degrees, multiply it by 180, and divide it by pi. Oh. And the number theta still should go there. And like I'm trying to resolve Greek letters for angles that are measured in radians right now, and d for angles measured in degrees. That doesn't have to be the case. There's nothing magic about those letters. Oh, maybe I should point this out. That symbol is the Greek letter theta. That being said, like, if a mathematician ever pronounces a Greek letter at you, know that that mathematician is mispronouncing the name of that Greek letter. Don't know what the right one is, but I've been told enough times by enough Greek language scholars that the pronunciation is wrong. Cool. So let's try to play this game. Let's suppose I give you a 30-degree angle. Do you think you could tell me its radian measure? Yeah, do it. once you have an answer, maybe do a quick compare with those around you. Yeah, I guess you can get a decimal approximation too. I'm not so interested in the decimal approximation this time. I'm interested in the exact value. So what are we getting?
0.523, 524.
Approximately 0.524.
Yeah.
I don't care about that number though. I want the exact value.
Pi divided by 6.
Pi divided by 6? Cool. And there's the answer I'm actually going to care about. That's something that we'll use a lot. By the end of this semester, if you haven't internalized that 30 degrees is pi over 6 radians, then I've done something wrong. How about pi over 5? Could you convert that to degrees? Yeah. What do I hear?
36.
Are you at 36 degrees? Is that exact? People agree? Should I actually do any of those computations? Groovy. So, pi over 5 is an angle that we just won't see as often. Not for any like super huge reason, it's just not one of the angles that I can compute trig functions of on the nose. This one will be though. A right angle. So there's a right angle. It's 90 degrees. How many radians is that? I hear a pi over 2? Yeah. So it'll be 90 degrees times pi radians per 180 degrees. Degrees cancel. 90 is half of 180. Cool. All right. So let's just see some things that you might be intuiting from this. A lot of times when we'll see a radian measure, we'll have a pi next to it. But is there any law that says that all angles in radian measure should have pi's next to them? No. Right, like this angle of 0.524 is a perfectly good angle to measure. Let's see an example where there is no pi. Let's suppose I give you angle measure of 1 radian, not pi radians, 1 radian. What's that in degrees? And you can give me a decimal approximation if you want. There's no pi next to it. So what do you do to get an angle in radians to degrees? What do I need to multiply and divide by? Multiply by 180, divide by pi. So 1 radian is 1 times multiplied by 180 and divide by pi degrees. Oh, cool. So that's just like 180 over pi. There's no simplification to be done. There's a pi in that denominator. What is that about? About 57.3 degrees. Cool. So sometimes angles just don't have pi's next to them, and that's fine. Any questions so far right now? So we have 3 ways of measuring angles. Maybe degree measure feels most natural in that numbers you expect to see will maybe be numbers that feel familiar. They'll just be like numbers between 0 and Usually it's between 0 and 90 degrees. Sometimes they'll be between 0 and 360 degrees. They can be negative, but that's okay. Radians will be somewhere between 0 and 2 pi most of the time, and 2 pi is like 6.2-ish. So that's like kind of awkward. But we're about to see why walking in radians is the best choice. You can get good geometry going on if you walk in radians. So, let's talk about sectors. So, here is an area formula. So start with a circle of a radius r, and draw a sector of angle theta in that circle. So, what's a sector? Well, it's a region like this. Draw two different radiuses of the same circle. Plural of radius is actually radii, but if I go around using the correct Latin pluralization, then I'll screw up the singular version. I'll accidentally say things like matrici or vortici, and I'd much rather say things like vortexes. Okay, but that's neither here nor there. There's a sector. The formula for the area of this sector of radius r and angle measure theta in radians is area equals radius squared times theta divided by 2. And maybe let's just use this to do something. So here's the first thing to do. Let's take a sector of angle pi over 3 and radius 4. Could you use that formula to just tell me what the area of that sector is? What'd you get? You said 8.37-ish. Are there any units specified in this problem that I should put in? Okay, so there's no need to put like square inches or anything, because that would just be wrong. There is no unit specified. What was the exact value you had?
$16 pi over 3, all divided by 2.
Yeah, so the 16 came from 4 squared times pi over 3, and then you divide that by 2. And 4 squared is in fact 16. Let's simplify that answer a little bit in addition to just giving the decimal approximation. It looks like there's division twice. What happens when you divide and then divide again? If you divide by 2 and then divide by 3, you just divided by 6. So this whole thing is the same thing as 16 pi over 6. See any common factors between the numerator and denominator? They're both even. Same thing as 8 pi over 3. There's the simplified exact value of this area. Let's also do this another way. There are 2 pi radians in the full circle. So pi over 3 radians will be 1/6 of the full circle. So let's try to do this using that idea instead, just to see if the formula works out correctly. What's the area of a circle? This is definitely just to like, how well do people remember their previous geometry class?
2 pi r squared.
Just pi r squared. The way to remember is that pi r not squared. Pi r round. Convert r squared. Good. Good. So the area of the full circle, area of the full circle is pi r squared, also known as, in this case, pi times 16. The radius is 4. This sector is 1/6 of the circle. So if the whole circle has area pi times 16, and I want 1/6 of the circle, how much area should there be? Or just how would I get that area? Divide by 6. Yeah. So the area of the sector sure looks like it's 16 pi, the area of the full circle, divided by 6. Oh, cool. Is that exactly the same thing as we just got? Nice. So that's also me trying to convince you that this formula is actually correct. The area of a sector, if the angle is measured in radians, is r squared times the angle measured divided by 2. Neato. Let's do one last one. Let's suppose that this time I give you an angle of 30 degrees. Same radius still 4. Let's try to compute the area of this sector. So do I have this already as an angle measured in radians? No, right now it's in degrees, but could we convert that to radians? Let's do that first. So first let's convert to radians. How many radians is 30 degrees? I hear a pi over 6. People agree? Did you do that by doing the computation or just remembering the previous page? It's on the previous page. That is pi over 6 radians. Now do we have the angle in radians? So we can use this area formula. Area is equal to r squared theta over 2 equals 16 times pi over 6 over 2. I find something we can simplify easily enough? Yeah. It'll wind up having a pi in the answer, but simplify that. Tell me what you get.
Pi over 3.
Right here, a 4 pi over 3. Do I hear a second? I see some seconds. Excellent. Should I go through the computation in detail from here? Cool. Seeing no hands. 4 pi over 3. And you know what? Just for the sake of adding this in, let's suppose that I gave you that the units in that radius were millimeters. How would that change the answer? All right, so this 16 would have a millimeter squared next to it now. So it'd be 4 pi over 3 millimeters squared. Cool. Neato. So here's one nice thing about walking in radian measure. There's an area formula if you walk in radian measure. There's also an area formula if you walk in degree measure on full revolutions. But that formula will just have an extra like pi over 180 or 180 over pi in it. Or maybe just a 1 over 2 pi if you're walking in revolutions. revolutions, or times 2 pi. The point is the formulas are all uglier if you don't walk in radians. And they are uglier by exactly the unit conversion. So instead, just convert everything to radians before you do anything geometric with them. Once you have them in radians, use them. Seem pretty okay? Nice. There's one last thing that I want to do with radians, and I'm actually feeling better about time than I usually am this lecture. That's weird. Let's talk about angular speed. So if you have like a gear that's spinning around, there's like 2 reasonable things you could ask about that gear. How often is my shoulder popping? That's not good. Like the point on my fingertip, how fast is that moving? What is its like linear speed? Inches per second. You can also ask, this point of rotation of my shoulder, how fast is it going in terms of radians per minute, degrees per minute, or like revolutions per minute? How can you convert between those 2 things? Because they're obviously related. If the point on my fingertip is spinning faster, then my shoulder has to be spinning faster. And that conversion is given, well, okay, I guess let's build these in. So the angular speed of a rotation in radians per second or degrees per second or whatever is given by, well, let's say it this way. How much of an angle is traced out divided by how much time it took. Right, like that's how you measure velocity. How much of something happens divided by how long it takes for it to happen. Right, like that's how you measure speed. If your car is traveling at 60 miles per hour, that means that if you wait 1 hour, the car has traveled 60 miles. So there's the angular speed. The letter I'll try to use for that is the Greek letter omega. Not that that's like super important. If you want to call that W, I won't be confused. The linear speed is given by exactly what you think it should be. How much distance is covered divided by how much time it takes. And then we're not talking about distance as the crow flies. We're talking about literally how much of an arc length does the point travel along the circle. If it goes all the way around the circle, you still count it as having traveled even though it got back to where it started. The relationship between linear and angular speed is as follows. The linear speed, v, is equal to the radius times the angular speed. Where here v is linear speed, omega is angular speed, and that r is the radius. And this formula only works if you're measuring angles in radians again. If you're measuring your angle in like hertz, which is revolutions per second, or like degrees per second or something, first you have to convert to radians. So your answer will have an extra like 2 pi or pi over 180. So don't try to remember like whether there's a 2 pi or a pi over 180 or exactly what extra multiplication factor there should be. Convert to radians first. That will get you the extra pi that should show up. So let's use this for some things. Closing examples. So let's suppose you have a 5-inch gear. So let's draw the picture. That is a perfectly circular gear. Its radius is 5 inches. And it's spinning around at 6 revolutions per minute. Maybe you want to abbreviate revolution per minute as RPM, but I won't. Let's just see if we have all the information we need. Do we know the angular speed of this spinning gear? revolutions per minute. Do we know the radius? Is that all the stuff we need to find the linear speed?
Yeah.
We have a formula. Linear speed is radius times angular speed. But I guess I better convert to radians first. How many radians is 6 revolutions? How many radians is 1 full revolution? 2 pi. So 1 full revolution is 2 pi radians. So how many radians is 6 full revolutions? 12 pi? The extra pi is important. And you whispered, and I'm bad at reading lips, so I'm not sure if you said the pi. Now do I have everything I need to get the linear speed of this thing? Yeah. It is radius, which is 5 inches, times 12 pi. And you might think I should be saying radians per minute, but remember, radians are already like a ratio of 2 distances. 1 radian is like 1 foot here divided by 1 foot there. So radians really have no units next to them once you get to distances. So I end up with 5 inches times 12 pi per minute. 5 times 12 is 60, right? Okay. 60 pi inches per minute. That feel pretty good? Could we go the other way? If you know the radius and the linear speed, could you find the angular speed? I think so. But that's not like, oh, that's not going to be till 4. Okay, let's get to 4. I have to do these first ones first, though. So let's suppose you have a gear, radius 2, spinning 30 degrees per minute. Let's compute its linear velocity. First things first, to get the angular speed in radians per minute. So, complete items 2 and 3 in that list. Compare with those around you. Tell me what you get. So, in the interest of time, what is the angular speed of this gear in radians per minute? 2 pi radians. There we go. And it's per minute, I think. Feel pretty good? So what's its linear speed? Well, what's the radius? 2, and there are no units given, so it's just 2, times pi over 6 per minute. So I guess that's pi over 3 per minute. So far, so good? So here's something you can now do. Let's suppose this gear of radius 2 is connected to that gear of radius 1. So like the teeth interweave. That means this gear of radius 1 has the same linear speed. That is, that thing has linear speed pi over 3 per minute. And put units on it if you want. Could we figure out the angular speed of that smaller gear? I think so. We could use the formula V equals R times omega. I know the linear speed, it's pi over 3 per minute, equals radius 1 times Omega. So what's omega? So you can also go the other way using this equation. You can use it to determine the angular speed if you know what it is. All right. So I am just about at time. In fact, I might be a minute past, but who's counting? I'll see you all tomorrow. Maybe take a look at that example on the very bottom where there's like this spinning wheel on a turret thing. And that has some like heavier unit conversions to be careful with. You might even have to look up some unit conversions. I think. Oh no, it's all in centimeters and kilometers. Ooh, let's stop the recording.